Assalamualaikum. Hi everyone. So in this video, we are still in chapter 1, reaction kinetics, but we're going to enter a new subtopic which is 1.3, factors affecting reaction rate. And this is the first part of 1.3. So what are we going to look today? I'm going to explain all the effect of following factors on the reaction, which is we're going to look on the effect of concentration or pressure, temperature, catalyst, and particle size, and then illustrate the effect of temperature on reaction rate using the Maxwell-Boltzmann distribution curve and compare the curve of the energy profile diagram for a reaction with and without catalyst. So without further ado, let's take a look on our lesson today. Factors affecting reaction rate. So what are the factors affecting our reaction rate? We have 5 different factors affecting the reaction rate, which is the first one we have here, concentration, pressure, particle size, temperature, and catalyst. So how does each of these factors affect our reaction rate? This is a table to explain the factors affecting the reaction rate. Okay, I made this table purposely so that it will be easier for you to write down the points when the question in exam asks what is the factors affecting the reaction rate. So we have 5 different factors affecting here, and if you look down here, the endpoint for each factors affecting is the same, which is frequency of effective collision will increase and the rate of reaction will increase. So as I have mentioned in our previous video, the rate of reaction is directly proportional to the effective collision. So how does effective collision occur? When the reactant has enough energy to react, which is our activation energy, minimum amount of energy, and then the reactant particles collide in a correct orientation. Then we have an effective collision. So how does we increase this effective collision to increase our rate? So let's take a look one by one. So the first one, we're going to look on concentration. Okay. So for concentration, as the concentration of the reactant increase, meaning we will have more particles of reactant present. So as more particles of reactant presence, the collision of the particle will increase. The frequency of the collision will increase. As the frequency of collision of particle increase, that's why we will have frequency of effective collision will increase. So in exam, the most important part that you need to write down is about the frequency of effective collision. You must not leave the word effective. This is the important part, because if you just mention about collision, it is not enough. Okay, maybe the particles, the reactant particles collide, but since it collide with not the correct orientation, so you will not form your product, there will be no rate of reaction. So that's why you need to mention effective collision. Okay, so that's the first one about concentration. Now let's take a look on the second effect, which is our pressure here. Okay, so pressure will increase by reducing the volume of the container. So when we talk about pressure, usually we will talk about gas particles. So how do we know pressure increase by reducing volume? This is from the previous semester that we learned our Boyle's law, where volume is inversely proportional to our pressure. So as pressure increase when the volume decrease. Okay, and then what happened when this occur? The concentration of the reactant will increases. Okay, how do we know that the concentration of reactant decreases? So when we look on the equation of concentration, so concentration is number of mole over volume. The number of mole here remain constant. Okay, number of mole constant. But as we decrease the volume, as the volume of the container increase, the concentration will increase. So since the concentration increase, what happened is the frequency of the effective collision will increase. So the rate of reaction will also increase. The next one, number 3, is the particle size. So when particle size decrease, the total surface area exposed for reaction will also increase. As the surface area increase, the frequency of effective collision will increase and the rate of reaction will increase. So this one, to explain this about the particle size, you can, the easiest one that you can imagine is when you want to make a sugar solution. Okay, where you have a sugar cube, okay, a big sugar cube, and then you have what we call as the gula pasir, the one that you use every day at your kitchen. Okay, when you try to dissolve these two sugars, the one that will dissolve first is this one. Okay, the one with the smaller particle size compared to the sugar cube. The next one is the effect of temperature. So for temperature, okay, how does temperature affect our rate of reaction? As the temperature increases, the molecules moving with higher speed, or we can say that the average kinetic energy of molecule will increase. So when we talk about temperature, we will always relate with the average kinetic energy. Higher temperature, more energy, it will collide, it will move faster, so the collision will increase. So that's why here the number of molecules possess kinetic energy equal or more to the activation energy will increase. So since we are talking about rate and it is related to the activation energy, so the temperature, as temperature increase, the amount of particle having the activation energy equal or more to the activation energy will increase. So that's why as this increase, the frequency of effective collision will also increase and the rate of reaction will also increase. So lastly, we have the effect of catalyst. So for catalyst, the first thing that you need to do is define what is catalyst. So this is the definition of catalyst: a substance that increases the rate of reaction without itself being consumed. Meaning, when we use a catalyst, the job of the catalyst is only to increase the rate of reaction. It will not itself being part of the chemical reaction to produce the product. Okay, how does catalyst work? It provides an alternative pathway with lower activation energy. So, since the reactant has a lower activation energy, so the amount of energy needed is less. So when the amount of energy needed is less, so the rate of reaction will increase. Why? The reactant particle can change into the product faster as the energy needed is less. So that's why number of molecules possess the kinetic energy more or equal to the activation energy will increase. Thus, frequency of effective collision will increase and the rate of reaction will also increase. Just now, we already discussed about the effect of temperature on the reaction rate. Now, what we're going to look is how do we discuss further the effect of temperature on the reaction rate by drawing one curve, by drawing a diagram. So what diagram are we going to look? We're going to look on the Maxwell-Boltzmann distribution curve. Okay, so how does this Maxwell-Boltzmann distribution curve looks like? So this is your Maxwell-Boltzmann distribution curve. So if you look closely, on the y-axis we have number of molecules, and then on the x-axis we have a kinetic energy. And this curve, you don't have to put any numbers into it. Okay, and this curve is used to compare between two different temperatures. One, we have a lower temperature and the other one is a higher temperature. So you need to mention this on your explanation later. So what you will see here is you will have two different curves. The first one, the blue one here, is for the lower temperature, and then the black one here is for the higher temperature, T1 and T2. Okay, so it's already stated here that T1 is bigger than T1 is smaller than T2. Okay, over here. So, the next part of this graph, as you can see here, there is one dotted line here showing the activation energy. Okay, meaning the area under the graph shows that the number of collision, the number of particles that collides, and the area under the graph after the activation energy shows that the number of molecules that have kinetic energy equal or more to the activation energy. So the only part of the particle that will produce the product is only this part. Okay, the one shaded here. So if you look at the shaded area, okay, the area under the graph after the activation energy, you can see that okay, the blue one is for T1, and then the cross one here, the blue lines here is for T2. So as you can see, the area under the graph for T1 is smaller compared to area under the graph for T2. Okay, and here we have E1 and E2 for average kinetic energy. Actually, you don't have to write down E1 and E2 in exam. Okay, enough if you just draw the two curves and then the area under the graph and the information around here. Okay, so this one, number of molecules with Ke more or equal to Ea at T1, number of molecules with Ke more or equal to Ea at T2, and then make a conclusion that molecules that have kinetic energy equal or more than the activation energy for T1 is smaller than T2. So, smaller than T2. So, what conclusion can we make here? So, the conclusion that we can make is, as the temperature increases, the average kinetic energy will increase, thus the frequency effective collision will increase and the rate of reaction will also increase. So, in exam, if the question asks you, okay, by a graphical method, describe the effect of temperature on reaction rate, meaning you need to draw this Maxwell-Boltzmann distribution curve. And about the temperature, if let's say in exam, the question gives you two temperatures, okay, maybe 30 degrees Celsius and 40 degrees Celsius. So you need to state, so T1 is 30 degrees Celsius and T2 is 40 degrees Celsius. So label accordingly. You can label at the curve. Okay, wherever the point of the curve. It's just to show that that's the temperature. So we're going to drawing the Maxwell-Boltzmann distribution curve is important. Okay. So let me show you step by step on how to draw the Maxwell-Boltzmann distribution curve. Okay, so let's start. So the first one, you need to have your axis, number of molecules, and kinetic energy. The second part is drawing the curve. So you need to make sure that you draw the curve with the area under the graph it looks like it's almost similar, the total area under the graph. So how to do that? So the first one, okay, let's say here I have two temperature. So I have temperature 1, 50 degrees Celsius, and then I have temperature 2, which is 70 degrees Celsius. So how I'm going to draw this? Okay, so let's start with the first curve. So your curve, you will start from 0 here and then draw one curve like this. Okay, where here, the highest point here, it will tell you that this is the average kinetic energy of most molecules. Okay, and then it will go down here. Okay, to show that the amount of particles that have kinetic energy, higher kinetic energy will be lesser. So this is your first curve. Okay, so draw it like this. And then to draw the second curve, okay, so let me try to draw it freehand here. Okay, we're going to look on the Maxwell-Boltzmann distribution curve. So let me draw it live for you. How does this Maxwell-Boltzmann distribution curve? So the second curve, you should start from 0 as well, but the curve will be like slightly lower, the peak will be slightly lower, and the size will be slightly wider from the first one. Okay, it's not. Okay, let me try that again. Okay, trying to get a very smooth curve for you guys. Okay, so this shall do. So if you look here, the area under the graph is like almost the same. By right, we should count the area under the graph, but since this is only a sketch, so what you need to do is you need to make sure that, okay, this, and then label. So this will be T1 50 degrees Celsius, and this one will be T2 70 degrees Celsius. So you need to label it like that. Okay, after that, you're going to label the activation energy. Okay, so for the activation energy, you will draw one line over here, okay, like this, and then label it as EA. Okay, after that, the shaded area under the graph. So for the shaded area, what you can do is, okay, let's say for 50 degrees Celsius, I put it as rounds like this. Okay, and then for the 70 degrees Celsius, I do a line like this. Okay, you need to make sure that it is clearly shown the difference between the shaded area for the 50 degrees Celsius and for the 70 degree Celsius. Okay, so let me move this one. So after that, what you need to do is you need to make some points over here, okay, a guidance to show that, okay, what does it mean by the circle one over here? What does it mean by the area over here? Okay, so make a pointer here. Okay, and then another one, just to show what are you trying to show actually, and then put, so number of molecules with Ke, more than EA at T1. Okay, and then you put the value 50 degrees Celsius. Okay, so the green one, number of molecules with Ke more or equal to activation energy at T2. Or simply you can just put, if you don't want to put T1 or T2, you can put at 50 degrees Celsius or at 70 degrees Celsius. Okay. But you need to make sure that clearly you have this information. Okay. If you just, let's say, the question doesn't give you any temperature, so it just give you T1 and T2. So you need to clearly state that T1 is smaller than T2, and then you can label on the curve here. Okay. So from here, we can make the conclusion that molecules that have Ke more or equal to the EA. Oh, I'm sorry. This is not small e, actually. It should be Ke, like this. Okay, sorry for my mistake. Kea for T1 is less than T2. So, this is what you will give in exam. Right now, let's further discuss the effect of catalyst on reaction rate. Okay, like temperature, for the effect of catalyst, it can also be shown by a diagram. Okay, what kind of diagram will we use for the effect of catalyst on reaction rate? So now, let's take a look. The one that we are going to draw for the effect of catalyst, we're going to draw the energy profile diagram, like the one that we learned from the previous video. Meaning here, to draw the energy profile diagram, again, you need to remember, it is based on either the reaction is exothermic or endothermic. Okay, draw that one first, and after that, we will draw another graph, another diagram inside the same one. Okay, so what do I mean by this? So let's take a look on the example that I give you. Okay, so this is our energy profile diagram. So in exam, the question will ask you, on the same diagram, draw the effect of catalyst towards the rate of reaction. So you will draw this one. So this is just the normal reaction rate. Okay, the normal energy profile diagram without addition of the catalyst. So if you look at this one, since the reactance is down here, meaning here we have an endothermic reaction. So just let me label it there, endothermic reaction. Okay, so let's focus on this one, this part here. So what you need to do is, okay, first you need to correct the arrow here. So the arrow supposed to be, okay, so let me correct this one first. Draw the arrow like this. Okay, just a single-headed arrow pointing upwards from the reactant to the product. Okay, next, if you look here, you have two curves. Okay, so the first one is the EA, the original one without the catalyst. Okay, and then the second one is with the catalyst. So in exam, if you feel it is too much to draw here, what you can do is, you can just simply say that this is without catalyst, and this one is with catalyst. Okay, since catalyst, how does catalyst work? It increases the rate of reaction by providing an alternative pathway for the reaction that has a lower activation energy. So that's why you will draw here a lower curve, okay, that has smaller activation energy, but the energy of the reactant and the energy of the product is still the same. So that's why here you will have the same delta H, just the difference is at the activation energy. Okay, so this is for endothermic reaction. So now, let's try to draw for exothermic reaction. Okay, so exothermic reaction. I will just draw freehand over here. Okay, so pardon my sketching. Okay, so you have here your potential energy. Okay, and then reaction progress. So let's start, since it's an exothermic reaction, so our reactant is up here. Okay, and then you will draw your product down here. Okay, so just label, let's say I have, so let's say I have A plus B to produce C. Okay, so the same thing you will label. Okay, here is delta H reaction, and then this is the activation energy. So you can draw it like this. So EA without catalyst. And then on the same diagram, you will draw for the one with catalyst. So you will start from here. Okay, at the end here, just draw a smaller curve and until down there towards C. Okay, and label. Okay, so let me take another color. Okay, so sorry. Okay, here towards here. Okay, you will label this as the EA with catalyst. Please make sure that you only draw one diagram, not two separate diagrams. Okay, if you draw two separate diagrams, so what happen is we cannot compare the actual, we cannot visualize what actually happened. Okay, because it is not up to scale, the scale is not the same. So by drawing in the same diagram, you can clearly see that, okay, the one with catalyst, we have lower activation energy, so the rate is higher, okay, compared to the the one without catalyst. Okay, so this will be the end for part 1 for 1.3. So I'll see you again on the next video on 1.3 part 2. Thank you.